So our next speaker will be Jeff Murugan from Cape Town, who will tell us about 2D quantum gravity. I don't know whether Jeff's ready to share his screen.
Yeah, I am. Just
hi, Jeff. Perfect.
Hi. Give me 1 second. Let me just make sure this works. Okay, this should.
Yeah, coming up.
Come online. Yeah.
Yeah, perfect. Thank you very much.
All right, great. Should I go ahead and start?
Yeah. Yes. Thank you, Jeff.
Excellent. Well, thank you very much to the organizers, and especially Yang for the kind invitation to talk. And I'm sure all of the other speakers, just sad that we're not able to meet in person in China. So when Yang invited me, he kind of, the same as with Joan Simons yesterday, informed me that this would be a very broad audience and that I should keep this in mind. And I had some difficulty selecting what to talk about, and came to the conclusion that it would be nice to talk about something that I'm just starting to think about, at least in this way. And so what I'm about to say is very much work in progress. In fact, most of what I'm about to talk about today is not new. It's certainly all covered in the existing literature. And in a sense, I want to tell you a little bit about some dots that I'm seeing. And I don't quite know how to connect the dots yet, but it seems like an intriguing possibility that these dots should be connected, and that they tell a very pretty story that stems from differential geometry to quantum gravity. On the other hand, they're dots that kind of beg to be connected, and they're dots that actually start off very nicely with the work of Chern, and a lot of my work actually involves things like Chern-Simons theory and Chern-Simons matter theory, but I thought I'd talk about something slightly different this time around. So this is work that I certainly was not familiar with of Chern's, that goes back to the 1980s. And what I will say is based for the most part on some really nice old work of Gegenberg and Kunststatter, and the rest is kind of work in progress. Okay, very good. So I'd like to tell you a little bit about a connection between work of Gegenberg and Kunststatter that links work of Chern-Tenenblat back to the Berkeley days of the 1980s to a really exciting set of things that people in the quantum gravity community, specifically in string theory, are thinking about these days, which goes by the name of Jackiw-Teitelboim gravity. So for those of you who are aware of this story, you'll know it's about low-dimensional quantum gravity. For those of you who aren't aware of the story, who perhaps came from a more general relativity point of view, or differential geometry perspective, will recognize the name also in the sense that I'll clarify a little bit later as we go along. Very good. So so let me tell you a little bit about S.S. Chern, and in particular his work on pseudospherical surfaces. So this goes back to 1986 and the work of Chern-Tenenblat, and it's in a beautiful piece of differential geometry. They really defined and studied a class of, and classified a class of PDEs that described pseudospherical surfaces. So pseudospherical surfaces, you may have seen many of these. They kind of look like this. This is just a poorly hand-drawn version, but there are many images that exist on the internet, and you can take a look. And what they are surfaces that are described by a set of partial differential equations. So for example, suppose I have some PDE and some variable phi, some PDE in a variable phi, and it depends on x, on t, phi and some finite set of derivatives that go up to, let's say, the lth t derivative and the k minus lth x derivative. So the PDE is defined by f of all of these things equals 0. We will say that the PDE describes a pseudospherical surface if a pseudospherical surface M, two-dimensional surface, if we can find some set of one forms, omega I, that can be expressed in the form some f of I1 dx plus f of I2 dt, with I running between 1 and 3. And the coefficients Fij are smooth. And the PDE describes a pseudospherical surface if the associated structure equations hold, if and only if phi solves the PDE. So this translates to what we in physics would call the flatness condition for the one form omega. Okay. What this means is that given some solution to the partial differential equation phi, I can use these one forms omega 1, 2, and 3 to construct some Levy-Civita connection, one form, omega 3, and some metric made up of the sum of squares of omega 1 and omega 2. And this will result in a pseudospherical surface with Gaussian curvature -1. So this is a key aspect that relates these pseudospherical surfaces to Jackiw-Teitelboim gravity, which I'll come to in a little bit. Okay, so given a differential equation with some solution of this particular form, I can construct a pseudospherical surface with Gaussian curvature -1. That's the key aspect of this. Okay, so what's this got to do with Jackiw-Teitelboim gravity? Well, the connection comes via a rather famous PDE, the Sine-Gordon equation, which most of us as physicists are familiar with. This is the kind of canonical equation that we learn about solitons from. Okay, so let me show you what the connection is to these pseudospherical surfaces, and in particular the work of Chern and Tenenblat, and then we'll connect the Sine-Gordon to Jackiw-Teitelboim. Again, these are all largely dots, and I don't quite understand yet how they connect to the current thinking about Jackiw-Teitelboim, but maybe we can talk about this a little later. So suppose I choose the one forms in a particular way. So I choose for the components of the one forms cos phi over 2 dx plus dt, sine phi over 2 dx minus dt, and phi x, meaning the derivative of phi with respect to x, over 2, and minus phi t for omega 1, omega 2, and omega 3 respectively. So then I write down my structure equations, and you can show with very little effort that the structure equations hold if and only if the variable phi of x and t satisfies the Sine-Gordon equation. Here, box is the two-dimensional Laplacian operator, D'Alembert operator. So box phi equals sine phi is the Sine-Gordon equation. Okay. An important point to note is that the choice of one forms is not unique. For example, I could instead choose for omega 1, omega 2, and omega 3, 1 over eta sine phi, eta dx plus 1 over eta cos phi, and just phi x dx for omega 1, omega 2, and omega 3. And this also solves the Sine-Gordon equation as long as phi is a non-zero real number. Eta is a non-zero real number. What this gives me is a one-parameter family of solutions, in fact. And in the context of nonlinear partial differential equations, this one parameter is what we would call the spectral parameter for the family of Sine-Gordon equations. In fact, the existence of such a one-parameter family of one forms is related to the fact that the Sine-Gordon equation is not only some partial differential equation that has solitons, it happens to be an integrable equation. And the integrability of the equation is a key feature of why we really prize the Sine-Gordon so much. in the context of physics. Okay. So let's say a little bit about the Sine-Gordon equation. In fact, what we have here from this relation between the Sine-Gordon and the pseudospherical surfaces of Gaussian curvature, constant Gaussian curvature -1, is a kind of a, and I say this tongue-in-cheek, ADS PDE correspondence, if you want, where given some solution to a PDE, being the Sine-Gordon equation, I can use that to construct anti-de Sitter, two-dimensional anti-de-Sitter metrics. So in this case, the Lorentzian version of the Sine-Gordon equation, where the operator, the differential operator acting on the left, is the D'Alembert operator in 2 dimensions, maps to Euclidean ADS2 and in a particular gauge. And the Euclidean Sine-Gordon, which is not an altogether familiar beast, we're more familiar with studying the standard Lorentzian Sine-Gordon, but the Euclidean Sine-Gordon maps to what we would call standard ADS2, again, in a particular set of coordinates. You can convert these coordinates to standard global coordinates or whatever you want. And in fact, we will do that in a little bit to show you some more of the connection. But there's this intriguing connection between a PDE, solutions to the PDE, and ADS2. Okay. Again, it's worth mentioning that the Sine-Gordon equation has some truly remarkable properties. For one, it's an integrable equation, and the integrability, as I said, is tied to this spectral parameter, which is reflected in an infinite tower of conserved charges that exist for the Sine-Gordon equation. It is, of course, a nonlinear hyperbolic PDE, and it's a hyperbolic PDE that possesses a rather rich spectrum of solitonic solutions. In fact, these solitonic solutions are going to play a key role in what I'd like to talk about now. And it's also worth mentioning that the quantum version of the Sine-Gordon is S-dual in the string theory sense of the word to the massive Thirring model. In fact, it is, if you want to learn about boson, if you want to learn about dualities, this is one of the simplest types of dualities that you would encounter, where the Sine-Gordon model maps to the massive Thirring model via bosonization of the fermions in the massive Thirring model. And this is, of course, an example of S-duality that takes place in the low energy theory. Very good. Another important aspect of the Sine-Gordon model is the fact that I can construct solutions of the Sine-Gordon. I can construct solitonic solutions of the Sine-Gordon starting from some seed solution. This goes by the name of Beckling transformations, and in fact, it's something that goes back a long ways away to some early work by Beckling in differential geometry, where the Beckling transformations are maps that take pseudospherical surfaces to other pseudospherical surfaces via a set of linear differential equations. And that's the key point here. To illustrate what I mean, I can take the simplest trivial example of these Beckling transformations, and it's certainly familiar to all of us. It's nothing but the Cauchy-Riemann equations. In fact, the Cauchy-Riemann equations are an example of what we would call an auto-Beckling transformation. So let me show you how that works. The point here is that the Cauchy-Riemann equations are a set of linear first-order DEs that relate some complex variable u, that relate to some variable u to some variable v via the x derivative of u equal to the y derivative of v, and the y derivative of u is minus the x derivative of v. Okay. By taking additional derivatives, I can show that if u and v satisfy these Cauchy-Riemann equations, then they also satisfy the fact that the Laplacian of u and the Laplacian of v must both vanish. In other words, u and v both satisfy the second order differential equation, the same second order differential equation, in fact, and are related by a set of first order linear DEs. This is, in fact, an example of a Beckling transformation in which the Beckling transformation maps a harmonic function to its harmonic conjugate. Okay. A less trivial example, and in fact the one that's important for us, is the Beckling transformation of the sine-Gordon equation. So here, imagine I have two variables, v and u, and they're related in the following way: that vx, v sub x, dv by dx, v sub x is u sub x plus 2k sine of v plus e over 2, and a similar equation for v sub y and u sub y. K here is an arbitrary real parameter. K here is an arbitrary complex parameter, and this will form the spectral parameter for the theory. Well, again, by taking derivatives, you can show without too much effort that each of u and v must satisfy the sine-Gordon equation in where x and y here are light cone coordinates for the sine-Gordon equation. In other words, this Beckling transformation that relates v and u maps the sine-Gordon equation, or pseudospherical surface, into another sine-Gordon equation, another pseudospherical surface. This is also an example of an auto-Beckling transformation because it maps sine-Gordon to sine-Gordon. It's not necessarily always the case. I happen to pick two examples in which the Beckling transformation maps the same pseudospherical surface to each other, but it could map different pseudospherical surfaces to each other. It could, by mapping different PDEs to each other. And of course, the thing that one would look for is for one of the PDEs to be significantly easier to solve than the other one. Okay, but in this case, why the Beckling transformation is so important for the sine-Gordon equation is because it's a solution generating transform. Meaning I can start off with some seed solution in the sine-Gordon equation, and I can use the Beckling transformation to generate other solutions of the sine-Gordon equation because it's precisely an auto-Beckling transformation. For example, u equals 0 is a trivial solution to the sine-Gordon equation because sine of 0 is 0. I can use u equals 0, take u equal to 0, and substitute it into the Beckling transformation to generate a highly non-trivial solution, this arctan of an exponential function. But the arctan of the exponential function is precisely what we would call the sine-Gordon kink. It is a solution that looks like a kink that starts at a particular value, asymptotically far away from 0 in the negative direction, and then asymptotes to another value in the positive direction. And it localizes a lump of energy at where the kink exists. Well, this arctan solution, this sine-Gordon kink, is precisely what we would call the one soliton solution of sine-Gordon. And it can be generated by this Beckling transformation. And in fact, you can do more than this. You can take V, this V here, sorry. You can take this V here, and you can substitute it back into the, Beckling transformation to generate a two-soliton solution. And you can keep going. In fact, you can generate n soliton solutions using this Beckling transformation explicitly. The solutions become more and more complicated, but they're still nevertheless explicitly constructed using this construction. Okay, so let's take a step back then and talk about gravity. And in particular, I want to talk about gravity in 2 dimensions, in 1+1 dimensions or 2+0 dimensions. And so the point here is that Einstein gravity in 3 dimensions, in 2+1 dimensions, is topological. It's pure Einstein gravity is non-dynamical. This is a famous result that goes back many years and was elaborated in a beautiful paper by Witten, in which he shows that 3-dimensional gravity is a Chern-Simons theory. But in 1+1 dimensions, in 2 dimensions, Einstein gravity satisfies the property that the Ricci tensor is identically equal to a half the Ricci curvature, Ricci scalar, times g mu nu. In other words, the Einstein tensor identically vanishes in 1+1 dimensions. And so in some sense, gravity, Einstein gravity, doesn't even exist in 1+1 dimensions. And so inspired by this statement, as well as some developments in string theory at the time, Roman Jackiw and Teitelboim independently suggested that one way out of this dilemma would be to couple in a dilaton, so that the resulting action would take the form 1/2g, where g is in 2 dimensions a dimensionless Newton constant, times the integral over the 2-dimensional manifold, let's say M2, root minus g tau, some dilaton, times r plus lambda, where of course this lambda here is a 2-dimensional cosmological constant. Now, it should be clear from the structure of this action that tau here acts as a Lagrange multiplier, enforcing the constraint that r plus lambda equals 0. So that the equations of motion that I get from functionally differentiating with respect to the dilaton is this should have an action on tau here. So this, sorry. So the point here is that I get 2 equations of motion by functionally differentiating with respect to the dilaton and with respect to the metric. And if I differentiate with respect to the dilaton, I get that r plus lambda must equal to 0. In other words, r must be minus lambda. This results in solutions that are ADS solutions, ADS2 solutions. And if I differentiate with respect to the metric, I get an equation for the dilaton that looks like this, where del mu here is the flat space derivative. Del mu here is the covariant derivative with respect to g mu nu. Well, the system has a remarkable set of properties. One is that the solutions of the Jackiw-Teitelboim gravity are all constant curvature solutions, which means that they're maximally symmetric solutions, which in turn implies that in 1+1 dimensions, the existence of 3 killing vectors for these solutions. These killing vectors are constructed from derivatives of the dilaton. So the dilaton acts as a sort of a potential in this case for the killing vectors. What's clear from this is that all solutions of the Jackiw-Teitelboim gravity are locally diffeomorphic to ADS2. But to specify a solution of the Jackiw-Teitelboim gravity, you don't necessarily just give me the metric like you would in Einstein gravity. I need the metric plus the dilaton. And this multiplet tells me that while all local solutions are diffeomorphic to ADS2, I can have globally distinct solutions. And in fact, one such globally distinct solution is the Jackiw-Teitelboim black hole, which I'll talk about just now. But first, it's worth pointing out that in the same way that 3-dimensional Einstein gravity is really a Chern-Simons gauge theory with some whose action is this Chern-Simons action with SO2,1 gauge group, and for some ISO 2,1 valued Chern-Simons form. Jackiw-Teitelboim gravity is can similarly be cast as a gauge theory. In this case, it would be what we call a BS gauge theory, with action given by the trace of phi, which is some SL2R valued scalar, times the curvature associated to some SL2R valued connection over a principal bundle of, on a principal bundle over spacetime. And the choice of components of the A to be the Fielbein and the spin connection reduces the equations of motion to these things for the EAs and for the omega, which necessarily means that any solution of this gauge theory satisfies that R of G, the Ricci scalar, must be -2, and I've normalized things so that R comes out to be -2. For G mu nu written in terms of the Fielbein in this way. In other words, any solution of the JT gauge theory is necessarily a solution of JT gravity. The reverse is, the converse is not necessarily true, but it won't concern us. Okay, so this brings me to a particular solution of JT gravity, which is a JT black hole. So, as I said, there are conserved quantities associated to the dilaton and the metric in JT gravity. This is the 3 killing vectors and an associated ADM-like mass. And from them, I can construct a black hole. This is the JT black hole that takes the following form with a linear dilaton. Okay. Some of the properties of this black hole is that it's actually a dimensional reduction of a more familiar 3-dimensional BTZ black hole. By just staring at the metric, you can see that it has an event horizon at r equal to the square root of m with ADM energy m over 2g. And the BTZ canonical singularity at r equals 0, because we're now in 1 + 1 dimension, there's no conical singularity, but it corresponds to the fact that when the dilaton vanishes, the effective Newton constant blows up. The point here is that the Sine-Gordon kink, and I don't have time to go into the specific construction, but the Sine-Gordon kink solution, this one soliton solution of the Sine-Gordon equation, determines a metric in some coordinate patch on M2, the solution of the JT gravity, in which we can always find a killing vector, K mu, that is time-like outside the event horizon, but becomes null in some interior point. In other words, the Sine-Gordon kink determines a black hole of the JT gravity. And you can show that you can show precisely where the coordinate singularity and the horizons lie in these one soliton solution coordinates, which map to, in critical coordinates, a picture like this. And so there's this very pretty correspondence between the Sine-Gordon kink and the JT classical black hole solution. And in fact, you can go even further if you're willing to be a little bit bold with your speculations and conjecture that, given any solution, which I can construct using this Beckling transformation, any soliton solution of the Sine-Gordon equation, one can find some corresponding JT black hole with a uniquely determined mass. So let's be bold and make some speculations then as to why this might be an interesting direction to think about. So suppose I have a JT black hole with some total energy E0. And I construct this JT black hole, or rather, I imagine that this JT black hole can be described by an n-soliton solution of the Sine-Gordon equation. I can calculate what that n-soliton solution has for its total energy. And in fact, these gentlemen back in the 1970s already managed to do this, to get an expression for the total energy. Here, the pi is the canonical momentum of the ith lump that makes up this n-soliton solution. And in fact, if I consider the rest energy by setting the pi is equal to 0, then the rest energy of this is just n over b, where n is the soliton number, the topological charge carried by this soliton, and beta here is the Sine-Gordon coupling constant, usually the coefficient of the cosine term in the action for the Sine-Gordon theory. Well, I have this lump of energy that's made up of an n-soliton solution. And the n-soliton solution I can think of as a bound state of some set of lower topological number solitons. The degeneracy of this solution, of this state, is the number of ways that I can form this n-soliton solution, this n-soliton configuration. In other words, it's the partition of n, the ways I can make an integer n from smaller numbers. Well, I have a formula for this partition, and this is the Hardy-Ramanujan formula, which says that for large n, the number of ways you can partition n goes like e to the pi times the square root of 2n over 3. Well, the numbers, the degeneracy of the state is what I can use to construct the entropy of the state. And the entropy of the state would go like the log of n, which is like pi times the square root of n, which is like pi times the square root of e naught. But this is precisely the Bekenstein, well, it's not precisely the Bekenstein-Hawking entropy. It's up to some factor of order 1. It is the Bekenstein-Hawking entropy of a JT black hole. And so this leads one to speculate that that there may well be a deep connection between this integrable field theory and gravity, specifically quantum gravity, in 1+1 dimensions. Or maybe I'm just reaching here. So let me conclude then with a brief discussion of the connection between Chern's work with Tenenblat on the theory of pseudospherical surfaces and what is really at the forefront of low-dimensional quantum gravity today. So clearly, Chern's work on pseudospherical surfaces kind of paved the way for much of the work on these soliton-generating transforms, Beckling transforms in integrable systems. And you can apply this to Sine-Gordon, as we did, or Liouville, etc. And there's a deep connection, it seems, to this Jackiw-Teitelboim gravity, which is a wonderful laboratory today to test ideas in two-dimensional quantum gravity. One of the reasons that we work, a significant chunk of the string theory community or ADS-CFT community are interested in this JT gravity is because of the ability to compute things like page curve using replica wormholes and Hawking radiation, and thinking of classical gravity as this averaging over some ensemble of quantum theories, etc. So it's a wonderful playground to test these ideas that are much more complicated in higher, more realistic dimensions, but really tell us something about the deep structure of quantum gravity. And via this relation to pseudospherical surfaces of constant negative curvature, it strikes me that these Sine-Gordon solitons, which emerge from the theory of integrable systems, provide an interesting realization of these black holes, and perhaps another set of tools with which to study these quantum gravities theories in lower dimensions that will hopefully have some feedback into the broader program of quantum gravity. And with that, I'd like to end by just saying thank you.
Thank you so much, Professor Murugan, for a very interesting talk. Lots of fascinating dots with connections emerging, so thank you. Does anybody have any questions?
Yes. Hello.
You mentioned, yeah, go for it.
I have a question. Yeah, so as we know that in the early 1990s, people study a lot of this 2D string theory gravity or even lower matrix model. So this JT gravity, what's the main difference from those study in the 1990s?
Let me see if I understand the question. Well, firstly, thanks for the question, Mitchin. This is one of these ideas that's recycled, and a lot of the work, and in fact, if you want to pick up those ideas on the relation to matrix models, the work to look at is the series of papers by Clifford Johnson. Clifford did a lot of work on matrix models and the relation to integrable systems and Beckling transformations back in the 90s, the connection to JT gravity these days came via the realization by Alexei Kitaev that the SYK model was dual in a low energy limit to JT gravity, where the Schwarzschild mode on the JT gravity maps to the Schwarzschild theory on Schwarzschild limit of the SYK model. And then there's been a resurgence of work on JT gravity, and related to what you said about the relations to string theory, the CGHS model, which is in some ways the flat space limit of JT gravity in 2 dimensions. And so there are very much connections between the 1990s matrix models and what people are studying today in JT gravity. And this is kind of part of the, I would like to understand how to connect those dots completely, which I don't at the moment.
I see. Okay, thank you.
That's the question. Hi, Jeff.
Hi, Deb.
So there are loads of very interesting calculations that you outline that people do. How many of those do you think will be you'd be able to extrapolate into non-JT gravity? So, for example, we're interested in page curves, thermodynamics, and then because of this, the calculable structure, you can then calculate these things in JT. But do you expect that that will actually carry over to more general cases? Or is it just a nice sandpit and that it won't carry over?
So let me answer in a parable. Last year when we had strings and we were trying to put together the meeting, there was this enormous amount of work that was going on, calculating page curves, and everybody was very excited. And I got a couple of emails saying, oh, maybe all these strings meetings, we'd like to introduce something like really groundbreaking, like you want the next string revolution coming out of all of these meetings, right? So somebody was like, oh, maybe this would be the meeting in which we nail down the information loss paradox, right? And that's because of all of the stuff that's been going on with replica wormholes, and we can calculate the page curve and stuff. So now we understand it. And so we set up this Friday as a panel discussion that had all the big players in this field, right? And we thought, okay, cool. Maybe this will be the announcement. And it turned out that nobody agreed on anything. So there's the replica wormholes group, and then there's Surat, and then there's Samir, and everybody's bringing different perspectives to the problem. And we realized that actually maybe that this is a really special system, and it is the sandpit, and we're learning lots of cool things about low-dimensional gravity, and it's not clear how much of it ports to four-dimensional to the four-dimensional story, right? But then there's this whole other perspective of BMS symmetries and what's happening on the horizon in 4 dimensions, and how this relates to what's going on the celestial sphere. And those seem to be disparate from what we're learning here. And so it's clear that this is, at least clear to me anyway, that this is a very special system. And integrable theories in general are set of measures 0 in the set of all theories that I would consider, right? And I think for me, yeah, I was kind of turned on to this idea of the connection to the Sine-Gordon system by a student of mine who happened to have encountered this paper and said, oh, look, you got me studying this JT stuff and understanding how chaos emerges in this story. But I found this paper and there's this whole other world of integrable systems that seems to be related to this. Do you know how it's related? And I'm like, I've never seen this before. It seems really interesting. But the fact that it's related to these integrable models tells me that it really is exceedingly special. And I don't know how much of this is generic, and I suspect not much.
Okay, thanks.
But it's still fun.